Just a few weeks back, scientists anticipated that 3I/Atlas, only our third confirmed interstellar guest, would glide silently by Mars. But then the unthinkable occurred. Over a mere 48 hours, this cosmic wanderer burst into activity, shining 6 times more intensely than comet simulations had forecasted, while forming a verdant carbon dioxide-laden haze spanning half the sun's width. At present, observatories on our planet stand powerless as Atlas hurtles toward Mars at close to 70 kilometers per second, fading from sight amid the sun's overwhelming light. What drives this apparent extraterrestrial voyager to defy all norms? Does it hint at groundbreaking physics, or conceal an even odder mystery? What's transpiring in the vicinity of Mars? And will anyone here manage to unravel it before it's too late? Right now, 3I/Atlas lingers roughly 2 astronomical units from the Sun, double the span between our world and its central star, or about 300 million kilometers distant. Presently, it's plunging closer at an astonishing 58 kilometers per second. That pace defies easy comprehension. It surpasses by more than twice the orbital speed of the swiftest planet in our system. Even Mercury, the quickest, circles at under 48 kilometers per second. 3I/Atlas could traverse the Earth-Moon divide in slightly more than an hour, compared to the 3 days required for Apollo cruise. As it nears perihelion late in October, its velocity will surge further, hitting almost 68 kilometers per second, a limit that strains the limits for typical bodies in the inner solar system. By contrast, the Parker Solar Probe, humanity's speediest creation, will top out around 200 kilometers per second, but only via prolonged gravitational slingshots and meticulous design. 3I/Atlas attains its momentum effortlessly, drawn by solar gravity along a hyperbolic trajectory. On the magnitude scale used in astronomy, 3I/Atlas now hits magnitude 12. Though this figure seems arcane, it holds tangible import. The dimmest stars detectable without aid top out near magnitude 6. Every increment on this logarithmic scale signals a major shift. A 5-magnitude gap equates to a 100-fold brightness variation. The shift from magnitude 16 to 12 for 3I/Atlas equates to roughly 40 times greater illumination. Still, at this intensity, the comet eludes unaided vision. It demands a moderate telescope under pristine, moonless conditions for hobbyists to spot it. To many, it appears as a faint blur, scarcely separable from the cosmic backdrop. The comet's luminosity stems from more than mere optics. It arises from the vast sunlight diffused by its swelling coma. The core of 3I/Atlas stays concealed, veiled in a dense shroud of vapor and particles. Projections of its diameter vary from a modest 0.3 kilometers to a heftier 5.6 kilometers. Enveloping the core, the coma, this luminous sheath, has ballooned to almost half the sun's breadth. Far from an illusion, this envelope constitutes a tangible entity, stretching hundreds of thousands of km, composed of solar-heated ices and debris turned to gas. It bounces and disperses sunlight on an unprecedented scale so far from the sun, setting 3I/Atlas apart from typical comets. Orbital models verify that 3I/Atlas traces a hyperbolic route. It remains unbound to the sun. This marks a solitary transit of our solar system, with no encore. Its minimal distance to Earth won't fall below 1.8 astronomical units, ruling out any collision or fragment hazards. The pressing matter is the brief chance to scrutinize such an interstellar interloper as it speeds through our domain, soon lost to solar brilliance. Every measure, separation, velocity, luminosity, positions 3I/Atlas well beyond the standard behaviors of solar system denizens. The figures evade straightforward parallels. With a Mars encounter looming, these details form the foundation, grounding the narrative in solid, immutable evidence. Mere hours after the illumination surge, the Comet Observation Database, COBS, buzzed with notifications. Observers in Australia submitted the initial highlighted readings, registering a 6-fold surge in radiance across 2 evenings. Did this signal a genuine flare-up, or merely optical distortion from photometric noise on October 3rd? 3I/Atlas will skim by Mars at around 30 million kilometers, near in astronomical scales, yet safely remote from peril to the crimson world or its satellites. The object's path drives it outward without pause, characterized by an eccentricity exceeding 1. This straightforward value indicates it's unattached. An interstellar entity executing a lone, unalterable sweep through the solar system prior to receding into the void. For our planet, the nearest pass has passed, staying above 1.8 astronomical units. In concrete distance, that's over 270 million kilometers, almost double the Earth-Sun gap. Expect no fragments, no collision peril, no shower of meteors. The sole imperative is gathering data before the observing slot closes. Yet that slot narrows rapidly. As 3I/Atlas charges inward, the alignment of its course works against terrestrial skywatchers. The separation angle from the comet to the Sun, termed solar elongation, the comet's visibility continues to diminish daily, with solar elongation shrinking steadily. By October 21st, this angle falls under 30 degrees, marking a pivotal limit. At that point, even top-tier telescopes find it hard to distinguish the comet's dim light amid the intense glow of the dusk sky. For typical skywatchers, the effective observation period ends in early October, coinciding with the comet's nearest pass by Mars. The schedule leaves little room for error. Perihelion occurs on October 29th or 30, as 3I/Atlas swings to within 1.36 to 1.4 astronomical units of the Sun. During this phase, its velocity surges to around 68 kilometers per second, and its outbursts are projected to hit their peak. However, from our planet's viewpoint, the comet vanishes into the Sun's brilliance, undetectable by the biggest ground-based instruments. This obscuration phase, lasting from early October into early November, ensures the comet's most intense development happens out of sight for direct earthly observation. Orbit calculations, drawing on data from countless sightings, detail every aspect of the comet's route with precision. The projections are clear-cut. 3I/Atlas won't come back. Its hyperbolic orbit ensures that unresolved questions from the next few weeks will linger indefinitely. The pressure stems not from any threat, but from the exceptional opportunity to observe an interstellar visitor engaging with our solar system, interacting with the Sun and planets, prior to its permanent departure. To prolong this view, the responsibility must now shift to probes orbiting Mars, each equipped with specialized sensors and poised to document parts of this transient event. The push for information kicked off as soon as 3I/Atlas deviated from its forecasted trajectory. Telescope coordinators worldwide launched a frantic effort against the clock and solar interference. As the comet's brightness spiked dramatically, key observatories triggered opportunistic observation modes. The Hubble Space Telescope, despite its heavy backlog, allocated an urgent slot for imaging in ultraviolet and visible light, snapping pictures as the coma expanded rapidly. HST teams had to carefully manage exposure risks of overexposure while adjusting settings in real time to match the comet's swift intensification. Shortly after, the James Webb Space Telescope gained a scarce, panel-sanctioned opportunity for mid-infrared analysis. On August 6th, JWST's NIR spec targeted the coma, detecting an elevated carbon dioxide-to-water ratio of about 7.6, well beyond typical levels for comets in our solar system. This discovery, relayed instantly to the Minor Planet Center and circulated via internal messaging groups, sparked a surge in demands for more spectral data. Next, the Gemini South Observatory in Chile shifted focus, securing a series of visible and near-infrared images. Gemini's expansive field of view and quick adaptability enabled monitoring of minor shifts in the coma's form and hue, despite nightly variations in the object's luminosity. At the same time, SPHERE-X, NASA's infrared sky mapping mission, tweaked its scanning rhythm to snag occasional views of the comet's changing emissions. Although SPHERE-X lacks features for swift tracking, its extensive spectral range offered a valuable foundation for observing gas releases across varying solar distances. Every site contributed distinct capabilities alongside its limitations. HST excelled at detailing subtle coma structures, but was confined to brief intervals. JWST provided superior infrared detection, yet its agenda was packed with rival priorities for the same time frame. Gemini's terrestrial position faced challenges from atmospheric conditions and the comet's decreasing solar separation. Aligning these resources demanded orchestration akin to asteroid defense drills rather than standard comet studies. Facility leaders balanced petitions from rival research groups as processing systems churned through data around the clock to share unprocessed images. Online discussions buzzed with arguments on optimal filters and durations, since no chance could be wasted. The impending solar interference heightened the tension. Once the comet entered the sun's blinding zone, terrestrial scopes would go dark for an extended stretch. The concluding observations, HSD's UV captures, JWST's CO2 profiles, Gemini's chromatic shots, would stand as Earth's ultimate documentation. As the transfer to Mars satellites approached, the terrestrial effort evolved into a showcase of international teamwork, extracting maximum insights from a fading subject. When solar dazzle renders Earth's instruments useless, Mars emerges as the solar system's premier vantage point. Probes around the rusty world abruptly take on the role of monitoring an unanticipated interloper. Every mission offers a tailored array of equipment, prompting engineers and researchers to improvise, reconfiguring tools, and vying for limited viewing times. HiRISE, the HiRISE instrument aboard NASA's Mars Reconnaissance Orbiter stands out for its capacity to discern items as tiny as a desktop from space. Offering a resolution of 0.3 meters per pixel, it could potentially detect the core of 3I/Atlas, provided the surrounding brightness and alignment of the orbit align favorably. However, pursuing a comet racing at 58 kilometers per second from distances of millions of kilometers challenges the capabilities of both equipment and algorithms to the extreme. Researchers from the University of Arizona and JPL conduct modeling runs, adjust shutter durations, and compete for optimal observation periods. Beyond simply failing to observe the comet, hazards include saturating the sensor or harming individual pixels if sunlight edges into the frame. ESA's Mars Express, which has been circling the planet since 2003, features the high-resolution stereo camera, known as HRSC. This tool shines in broad-area, multi-perspective photography, perfect for documenting the entire expanse of a comet's hazy envelope and trailing stream. Its spectral filters assist in distinguishing particulate matter from vapors, and paired stereo images might uncover faint depth variations within the growing nebula. The HRSC control group in Germany collaborates with Earth-based stargazers to schedule shots when 3I/Atlas nears Mars's path around the Sun. The Trace Gas Orbiter, or TGO, from the ExoMars program includes CASIS, a system for color and stereo surface photography, along with NOMAD, an array of analyzers crafted to identify subtle gases in the air. Though CASIS targets Martian rock formations, it can pivot to photograph the comet's haze across various wavelengths. Its quick capture mode enables monitoring shifts in luminosity and form over a brief encounter. NOMAD specializes in tracing faint elements such as CO2, H2O, and uncommon organic compounds. Directing its sensors toward 3I/Atlas, scientists aim to verify the heightened CO2 concentrations initially noted by JWST and hunt for molecular markers unseen in comets from our solar neighborhood. NASA's MAVEN probe contributes a unique vantage, relying on its ultraviolet spectrograph to capture signals from oxygen and carbon atoms, as its plasma detectors assess the solar wind's engagement with the comet's ejected material. MAVEN's observations might clarify if the haze's emerald radiance stems from oxygen atoms or rarer mechanisms. Positioned to probe Mars's uppermost layers, its trajectory offers ideal positions to view the comet's transit from varied directions. Control hubs across the United States and Europe hold urgent sessions, balancing the dangers of redirecting tools from standard planetary research. Securing any viewing opportunity involves discussions between technicians, lead researchers, and oversight leaders. Protective measures remain rigorous. Sensors avoid straight-on solar exposure. Analyzers require precise tuning, and particle threat assessments get thorough reviews. At times, code updates deploy right before activation to unlock fresh pursuit functions or bypass standard safeguards. No individual satellite can document the complete narrative of 3I/Atlas alone. Collectively, this global fleet creates a virtual telescope, merging visual captures, spectral scans, and particle readings from diverse paths and regions. Cleverness emerges not merely from the tech, but from the swift teamwork among groups unfamiliar with this comet just weeks ago. With ground telescopes losing sight, the duty of unraveling this extrasolar guest shifts to these automated sentinels around Mars, each ready to collect insights that might transform our grasp of icy wanderers and the compositions of bodies from outside our system. The hues in a comet's haze serve as a molecular barcode, formed by solar rays and the evaporating frosts from its heart. In September, 3I/Atlas astonished skywatchers when its haze evolved from a subdued crimson to a striking emerald. This alteration hinted at peculiar activity buried inside its swelling sheath. The haze's vast scale proved astonishing, stretching almost halfway across the sun's width, exceeding 600,000 kilometers in extent. Far from an imaging artifact or lighting quirk, the emerald sheen was genuine and required interpretation. Classically, emerald-hued comets get their tint from C2 molecules, which glow in the swan bands around 510 nanometers under solar illumination. But as experts examined records from Gemini, VLT, and JWST, the anticipated C2 signals were absent. No swan bands appeared, no trace of the typical carbon profile, despite the haze's increasing brilliance. Rather, the readings suggested an alternative source. JWST's observations from August showed a CO2 to H2O proportion of roughly 7:6, a remarkable figure well above norms for local comets, where ice usually prevails. This discovery refocused interest on oxygen atoms, particularly the prohibited OI line at 5,577 angstroms. This emerald wavelength emerges when UV light and high-energy electrons dismantle CO2 and H2O, releasing oxygen that releases green light while settling from an unstable energy level. Within the thick, CO2-laden haze of 3I/Atlas, solar UV and photoelectrons function as accelerators, converting the zone into a generator of emerald OI output. Benchtop tests and prior comet analyses back this mechanism. Process, yet 2I/Borisov pushes the boundaries further. Remarkably, even at a distance of 2 astronomical units from the Sun, the environment favors this process overwhelmingly, eclipsing the scattered dust continuum and generating the haunting emerald radiance that now characterizes the comet's look. Other theories were explored. Scientists hunted for CO fluorescence, particle scattering, and unusual plasma phenomena. However, the scarcity of CO and the steady dust signature ruled those out. The discussion played out live, with experts exchanging unprocessed spectra and adjustment codes, scrutinizing each fresh dataset for signs of C2 or additional carbon molecules. In the end, though, agreement formed around atomic oxygen as the primary force. The sequence of events was telling. The verdant stage emerged right when CO2 emissions spiked, and as the comet passed the point where solar ultraviolet rays could readily dismantle molecules in the widening coma. Dr. Lena Sato, the principal spectroscopist on the JWST team, likened the effort to pursuing an elusive quarry with an ever-changing nature. Every spectral reading depicted a dynamic setup where chemical reactions and physical forces clashed on an unprecedented scale. The missing C2 didn't signal defeat. Rather, it pointed to 2I/Borisov behaving by principles alien to comets in our solar system. That emerald light turned into its hallmark, a sign of interstellar reactions and primordial ice forged in a distant star's birthplace. The mystery lingers. With the coma shifting and Mars probes gearing up for fresh scans, the quest for conclusive spectral signatures, like C2 or odder ones, persists. Each reading might uncover if 2I/Borisov is merely a comet stretched to its extremes or a harbinger bearing enigmas from outside our cosmic backyard. The following inquiry: how does this chemical makeup influence the comet's form? And what could the backward tale disclose about the dynamics molding this extraterrestrial guest? A sunward streak cuts across the coma of 2I/Borisov, defying the standard view of a comet's tail. Rather than streaming away from the sun, this backward tail aims directly at it, apparent in Hubble snapshots and Earth-bound observatories alike. The common account, a visual illusion as Earth aligns with the comet's orbit, fails here. The alignment doesn't match, and the backward tail's endurance over weeks suggests something more profound. Experts in plasma and dynamics have zeroed in on the underlying processes. 2I/Borisov is ruled by carbon dioxide, not ice, with its venting highly irregular. Solar rays strike the core at a sharp slant, propelling streams of vapor and particles, chiefly from the sun-facing flank. This lopsided release propels hefty dust particles outward, but asymmetrically. The most powerful bursts happen in the brightest sunlight zones, extending a frost boundary deeper toward the sun than in ordinary comets. Particles ejected along that line are larger and less speedy, enduring radiation pressure and thermal stress for extended periods. Consequently, a genuine structural backward tail emerges, a curve of substantial particles that endures for tens of thousands of kilometers before eventual vaporization. Simulations show these particles measure at least 10 microns in diameter, massive enough to withstand the solar wind and maintain their sun-directed trajectory. Their longevity hinges on dimensions and composition. While CO2 frost evaporates swiftly, particles blended with dimmer, more stable substances can endure sufficiently to form the noted trait. The backward tail's luminosity fades sharply along its length, aligning with projections for particles gradually eroded by solar rays, beyond mere spatial dispersion. Magnetic influences introduce further layers. As the coma grows, it serves as a laboratory for plasma engagements. Electrified dust particles clash with the solar wind and the comet's emissions, forming tight flows and protrusions that warp the backward tail. Nonetheless, for 2I/Borisov, the key sunward element stems from particle durability and directional jets, not rare plasma behaviors. The ionic tail, molded by the interplanetary magnetic field, extends away from the sun predictably, distinctly apart from the backward tail's route. Speculation has touched on artificial origins, constructed forms, self-assembling plasma, or even alien tech, but evidence dismisses such ideas. All traits align with established cometary science, albeit strained by the object's peculiar composition and vigor. Dr. Rafael Ortiz, plasma specialist from the Mars Orbiter effort, captures it neatly. To confirm the remarkable, first eliminate the routine. Thus far, the backward tail stands as a victory for standard dynamics. The true trial lies ahead. As 2I/Borisov swings around the Sun and Mars craft collect intel, projections on particle dimensions, jet directionality, and plasma links will undergo rigorous testing. Should the backward tail diminish or shatter as forecasted for CO2-propelled particles, the argument for a natural basis solidifies. Otherwise, novel principles might emerge. Beyond perihelion, 2I/Borisov enters its wildest stage. The mod scientists are divided into factions, each harboring distinct predictions for the comet's trajectory ahead. Certain experts anticipate a gradual dimming, with luminosity waning as unstable ices deplete and the surrounding envelope contracts, ultimately yielding just a dim trace that wanders off into space. In contrast, some caution about an ultimate burst of light, ignited by untapped reservoirs of carbon dioxide or an abrupt crumbling of the core, reminiscent of comets that have shattered beneath the sun's relentless pull. A further option appears on the agenda of every orbital specialist: dissolution. Should the core prove as riddled with voids and fissures as its erratic behavior implies, the closest solar approach might trigger its fragmentation, hurling debris that momentarily intensifies the brightness profile prior to dissolving into emptiness. Dr. Mara Valente, an orbital analyst monitoring the phenomenon, portrays the upcoming period as a critical examination for all hypotheses concerning nomadic bodies from deep space. Her team's computational models outline numerous pathways, linked to precise indicators. A steady reduction in luminosity suggests routine vapor release. Unpredictable surges or abrupt plunges may indicate structural failure. An enduring verdant envelope following the solar closest point could indicate substantial reserves of carbon dioxide-laden frost, whereas a swift transition in hue toward crimson or azure tones might expose the depletion of those reactive strata. The implications extend far past the destiny of one celestial body. 32/Atlas serves as a messenger from a remote stellar domain, bearing the chemical makeup and architecture shaped in a far-off cradle. Its actions challenge the boundaries of cometary mechanics, probing how embedded frosts endure voyages across the void, the ways in which particles and vapors engage with solar currents, and the accuracy of our frameworks in forecasting the existences of entities that linger for eons amid the stars. Whether it dims, erupts, or shatters, each result supplies insights to bolster defenses against cosmic hazards, sharpening our methods for detecting and deciphering incoming visitors that could eventually present genuine dangers. Outlandish notions, ranging from artificial scouts to sentient energy forms, hover at the periphery. Thus far, no proof backs these assertions, yet the principles of inquiry require thorough scrutiny. Anomalies warrant evaluation through conventional mechanisms prior to resorting to the unconventional. The encounter with Mars and the solar proximity phase establish an exceptional testing ground, where theoretical forecasts confront actual occurrences and the line between established knowledge and potential discoveries is probed instantaneously. Critical benchmarks are already highlighted in schedules. Releases from Mars satellites arrive in early October. The solar closest approach falls on October 29th and 30th, and terrestrial observations resume in November. The forthcoming period will determine which frameworks endure and which demand revision. At present, the narrative of 32/Atlas unfolds as an ongoing trial racing across cosmic expanses. With each fresh datum, an opportunity emerges to peer into the mechanics governing realms outside our solar realm. Despite employing the finest tools, certain stellar guests depart with enigmas outweighing resolutions.